Okay, so in this video we want to use Taylor polynomials to approximate the cube root of 24. The cube root of 24. In fact, we want to use a third degree Taylor polynomial to accomplish this task. So we could use lots of cube roots. We want to find one that we know kind of precisely, and that's pretty close to 24. And the cube root that satisfies that is cube root of 27. So I'm going to decide to, for the best accuracy, 27 is the nicest cube root I know exactly. That's close to 24. So I'm going to center my polynomial around a equals 27. So this is not a Maclaurin polynomial now because it's not centered around 0. We're going to center this around 27. Okay, so to do the Taylor polynomial, we're going to need to know the first three derivatives of the cube root function. So, of course, our function itself is cube root. Our derivative would be 1/3 x to the minus 2/3. Our second derivative would be negative 2/9 x to the negative 5/3. And finally, our third derivative would be a positive 10 over 27 x to the negative 8/3. And then what we're going to need to do is evaluate these not at 0, not at 1 like we did in other problems, but at 27. So of course, f of 27 is just 3. That's our constant term. Okay, the next term, we're going to evaluate this thing at 3. If we put 3 in here, raising it to the 1, so of course it's negative 2/3, so it's going to really be in the bottom, but bear with me here. First, raising it to the 1/3 power, cube root of 27 will be 3, but then it's going to be squared, which will make it 9, but then it needs to, because of the negative exponent, it needs to go in the bottom, so we're going to really have 1/3 times 1/9 is going to be 1 over 27, will be our second coefficient in our polynomial. And then we continue doing the same thing here. Evaluate this at 27. Cube root would make it 3. It's then going to be raised to the 5th power, which would make it 243. And then go into the bottom with the 9. And we're actually going to get negative 2 over 2187, which is actually 3 to the 7th power. Okay, and then same thing with the last one, evaluating that at 27. The 1/3 part will make that 3. Then you're going to have 3 to the 8th, but it's going into the bottom. So you're actually going to have 10 over 3 to the 8th plus 3 to the 3rd, be 3 to the 11th, which is actually going to be 10 over 177,147. 147. And so those are our coefficients, and it'll be centered around x equals 27. So our terms are going to be x minus 27, x minus 27 squared, and x minus 27 cubed with these coefficients. Again, remember, the second derivative we divide by 2, third derivative we divide by 6. So as we write that out now, first two are pretty straightforward. 3 plus 1/27, x minus 27, and then minus. Now, that's going to be divided by 2 factorial, so it's actually just going to become minus 1 over 2187, x minus 27 squared, and then plus 10 over 177, 147 times 1/6. I just didn't bother simplifying that because we're plugging this right into a calculator here in a moment, times x minus 27 to the 3rd. Okay, and then we're going to evaluate this at the point we want to approximate, which is cube root of 24. Cube root of 24. So we're going to go in and plug 24 in. So we'll have 3 plus 1/27 times 24 minus 27. Minus that stuff times 24 minus 27 squared. Plus all this stuff times 24 minus 27 to the third power. And when we do that, we should get 2.88452. 2.88452, which you can compare, if you want, to the actual cube root of 24. The actual cube root of 24 is 2.884499. So 44949. And so it gets pretty accurate, at least to about 3 decimal places there, this cube root approximation. And so the final thing I want to show you here is the graph of this third degree approximation connected with the cube root here. And you can see it seems to be fairly accurate. Now I'm kind of zoomed out here on the x-axis, but definitely seems to be fairly close, at least for values around our pivot point of 27. The graph at least looks like it's getting fairly close. We saw our answer at 24 was pretty accurate. Okay, so that's Taylor polynomials and using them to approximate certain functions.